So let me briefly recap. So we are on level 2. So we start from a quiver, and then to this one we associate, well, first of all, let's say the stack of representation of this quiver. Let me say. This is the dimension, this is a smooth stack, okay, smooth. It's the stack of objects in some category of global dimension 1, nice category of global dimension 1. And then we associate the cotangent stack. And this is also not so bad. This is quasi-smooth. And so let's say just by looking at the quiver, we get some information about the K0. Here we get information about the whole algebra, either over FQ or this geometric whole algebra that I denoted K or K graded. And here now we want to get an understanding of an algebra structure on the entire homology of two things. First of all, this Lustig nilpotent variety. This is Lagrangian in T star rep Q. And we also want to understand the entire T star rep Q. And so these turn out to also have algebra structures that I will define. And so my plan for today is to tell you roughly what is known about these, at least what I know about these. Maybe not everything and maybe not in all detail, but still give you some kind of overview. And in the last part of the talk, explain what is known. The situation is not as well understood by far. When instead of a quiver, we start with another nice category of global dimension 1, namely coherent sheaves on curves, on smooth projective curves, let's say. OK, so finally, in my fourth lecture, I can define what is this Coha after trying to motivate it for so long. So Coha, 2D Coha. OK, there are other versions of Coha. This is the 2D Coha. So we consider, so first of all, it will be slightly clearer, I think. Instead of working with cotangent, one can actually realize this cotangent as modules over a certain algebra. Okay, maybe let me just introduce the pre-projective algebra. So Shivang introduced it yesterday in his Gong talk. So, well, simply from the quiver Q, we associate the quiver. This is the quiver with vertex set I, edge set E. This is the quiver with the same vertices, but now I double every arrow. Okay, for every arrow, I replace it by a pair of arrows going in opposite directions between the same two vertices. And so here we had this path algebra. Let's work with a C. So Yokinobu introduced it. This is generated by all the paths. Okay, this is the span of all the paths in Q, and as such, it is generated. Okay, let me try this. This is generated by, well, you have the idempotent, and then you have XE for E and edge. And the idempotents correspond to vertices. Okay? So the pre-projective algebra is a certain quotient of the path algebra of the double quiver. All right, so let me define that. Pi Q is the path algebra of the double quiver. So we consider all paths in the double quiver, which means that this is definitely going to be infinite dimensional, this one. And then we quotient out by some relations, and the relations are simply written like that. Sum of commutators is equal to 0. You should understand this as a bunch of relations, one for every vertex. Okay, you can multiply this on the left, on the right by the idempotence, and then you will get a bunch of relations. So, and in fact, this is just a moment map equation. Okay. So all this is to say that, very easy to check, that in fact T star rep Q, this is equal to the stack of representations of pi q. For every dimension vector D, we have this isomorphism, in fact, equivalence of derived stacks. Okay, so I will, instead of writing this, I will work with this one. Doesn't change anything. But maybe it makes the induction diagram a little more easy to imagine. So in order to define the product, we do the same induction diagram as before, right? In order to define all the products that I did define in level 1. But now we replace the path algebra of Q by this pre-projective algebra. Okay. So we get rep D1 pi Q rep D2 pi Q. Here we have this rep extension, so it counts extensions. Again, this is the stack parameterizing inclusion of one representation of pi Q of dimension D2 into one representation of pi Q of dimension D1 plus D2. Okay, and then I have this map. Okay, let's call this Q, let's call this P. So, well, if you think about it, oops, pi Q. So this map here is still some quartz scheme. Okay, it's a quartz scheme, or it's a Grassmannian, but now it's not a Grassmannian of sub-representations of the path algebra. It's a Grassmannian of sub-representations of pi Q. But of course, if all the relations are satisfied, including the new relations that we added on, then of course in any subspace stable by all the maps, the relations will still hold. So this map is just base changed from the map from the one we saw for CQ for Q bar. Okay, so this one is proper. This one is proper, and this one now is not smooth anymore. So if you remember, the cotangent stack to the stack of representation of Q was quasi-smooth. Okay, so this is quasi-smooth, this is quasi-smooth, and in fact, the map itself, Q, is also quasi-smooth. So let me try to explain why. So this is this we can view as the total space of if we include the derived structure of R hom from ED1, ED2 shifted by 1. So if you remember the tangent complex to rep D pi Q, this was the R hom, the total space. No, the tangent complex was R hom from ED1, ED2 shifted by ED1, ED1 shifted by 1. Okay, and the same thing here. And somehow this map is well, if I draw a picture like that, this is not to be taken too literally. I have R hom ED1, ED1, maybe ED2. ED2 shifted by 1. Here I have R hom ED2, ED2 shifted by 1. And here I have R hom ED1, ED2 shifted by 1. And here I have 0. So this is what the cotangent complex of this stack looks like. Okay, we have the deformation of each of these. And then we also have the extension between them. And that fits nicely into this matrix. Okay, so this is the total space of this map. And of course, this lives over this is a complex over these product of stacks, rep d1 pi q, rep d2 pi q.
Olivier, d1 is the dimension of the quotient or the subspace?
D1 is the quotient. This is d2, stable. Okay. Oops, this is d1. Thank you. Okay. So we are in the situation where this map Q now, it's not it's the projection to a base of the total space of a three-term complex. Okay, in the case of in the previous case of the geometric Hall algebra, it was a two-term complex. We just had hom and x1. Now we have hom, x1, and x2. Okay, but turns out that there exists a natural pullback map between the homology of, say, x to the homology. There's a shift plus 2 times the dimension of f of y for any quasi-smooth morphism f from x to y, okay, of derived stacks. So the formalism in general, you can find it in some work of Adil Khan. But in this particular setup, it's a little bit easier. And so I will maybe spend 3 minutes telling you what you are doing in this particular case. So, okay, so concretely, you have your three-term complex. So you represent, and we can do it globally. Okay, these are all nice quasi-compact stacks, and the quiver presentation just gives you directly a way to represent this R hom complex. So represent R hom from ED1, ED2 bracket 1 as a three-term complex of vector bundles. So let's say E minus 1, E0, E1. Okay, and then we can look at just the stupid truncation. Okay, the stupid truncation. E minus 1, E0. So let me say that the total space of such a complex, when you take the classical truncation, let's call this map B. Okay, so the classical truncation of the total space of such a complex is E minus 1 is the total space, let's say, of E minus 1 and the kernel of B. Okay, this is just a coherent sheaf now, but this is the total space of that. And the derived structure is exactly the co-kernel of this map. So if we throw away the derived structure, we really have the quotient of kernel of B divided by the action of this vector bundle. Okay, so now we can do the pullback in two ways without really appealing to the derived structure, so it seems. We can say, okay, I have the total space of E minus 1 to E0. Okay, and then inside of this, I have the classical truncation of the thing I want. Maybe let's just write the total space of E minus 1 kernel of B. And there, I just pull back, I just push forward to this product of rep pi q d1 rep pi q d2. Okay, and now this is smooth. So I can do the pullback. Okay, and this is inclusion of a zero section. A zero section of a vector bundle. The vector bundle is simply the pullback over this space of E minus 1, okay, which has a section given by B. Of a section, this is B, of a vector bundle. And so here, so for the first one, let's say this is Q1, let's say Q2. So there exists a pullback Q1 because Q1 is smooth. And there exists a refined Gisin pullback, let's say Q2 shriek, because it is the inclusion of the zero section of a vector bundle. Okay, so you can find this in Fulton intersection theory. And so if you don't want to appeal to this derived machinery, which is, of course, it's perfect, but you can also realize this pullback more concretely like that. Okay. All right, so in any case, we can do a proper push forward and we can do a quasi-smooth pullback. So we can define the product. All right. So let me just state the theorem. So there are many names here that one should put because this algebra structure was built, step by step. So yeah, I have to put all the names. So Eric and I, we did it in the case of some particular quivers because that's what we needed. And then Yaping Yang and Gufang Zhao, they did it for an arbitrary quiver and actually also for other cohomology theories for which you can apply the same machinery. No, actually for quivers, that's it. So yes, H star rep Q and the product given by pi Q. Thank you. This is an associative algebra. Is a graded associative algebra. There's a small thing you need to do on the grading. You need to shift a little bit the grading. So maybe I should say direct sum over D, and you shift by this Euler form, and then it is really a graded associative algebra. Okay, and the same thing, maybe I should say 1 and 2, same thing for the homology of the nilpotent. Okay, just the same thing for the homology of the nilpotent Lustig Lagrangian. Okay, so the aim is to understand what this algebra is.
And also equivalent,
And also, yes, and 3, you can turn on, thank you, equivariant parameters. So you can turn on a torus action. So if you remember last time, I described a large torus that could act on all these stacks, and so you get indeed you get HT star rep pi q as a H star T algebra. Okay. All right. So, what do we know? Well, we know in the case of lambda. So what do we know for the moment? Let's say we know the size of these algebras, lambda or rep pi q. This is given by Katz's polynomials. Okay. Then we know that inside of this one, there is a top piece, okay, which is independent of the torus action. And this is known, corresponds to the degree 0 term of the Katz's polynomial. And we know that this one, at least as a vector space, is the enveloping algebra of a Lie algebra, namely the Kac-Moody algebra associated to the quiver. So let me state right away Lucien's theorem. It says that the map, this characteristic cycle map, that goes from this graded Grothendieck group, remember we specialized to -1, and we know it's an isomorphism with this H top of lambda. This is actually an algebra isomorphism. Okay, this is an algebra isomorphism, and so we wonder what is the rest of the algebra. Okay, we have a natural extension of the enveloping algebra of this Kac-Moody algebra, and moreover, it comes with a deformation because all these quantum parameters t in here, they provide us a deformation. So we lost some deformation through this characteristic cycle map, but we actually gained many by working with equivariant cohomology. Okay. All right. So let me say right away that understanding the precise structure of this algebra or this algebra over, in the integral form, so considering as the integral form over this ring, this is very hard. Shivang gave a talk yesterday where he explained the case of the cyclic quiver. For finite type quivers, this is okay, but beyond these, it's really complicated. But we can simplify already our life. Sorry, Shivang, we just kill the integral structure and we just work over the fraction field. And this allows us to, so we localize, so easier. We work over the fraction field of H star t. And so it means that we will consider the localized version. We just tensor over ht by the fraction field. And then we have the direct image map. And because all the fixed points are inside the Lagrangian, we can actually identify the two. Okay. So we replace this problem of nilpotent versus non-nilpotent. It's an interesting question, but in order to just understand the structure of the algebra, if we localize, we can ignore that. Okay. So let me tell you some theorems about these algebras that we know. So first of all, expectation. What is the expectation? Expectation is that these are some kind of deformation. So yeah, let me just work with lambda now. Is a deformation of, well, it's an extension. Let's call it G tilde of, let's say, G tilde bracket U of G bracket U. Okay, because if you remember, the Hilbert series of H star T lambda or H star T rep Q was exactly the Hilbert series of the enveloping algebra of not G or not G tilde, but actually a loop algebra. Okay, so such things are usually called Yangians. So there are many different versions of Yangians. Hopefully they're all the same. But when you say Yangian, it's still an unprecise statement today. But OK, so expectation is that these are Yangians. And Yangians can be, in particular, defined by generators and relations, the Strinfeld relations. And if you look at them for the first time, you just want to change areas and start doing logic, maybe, or I don't know. So I will not write any relation at all, but I will just say that there's a theorem that gives a presentation of this algebra in terms of generators and relations. And they're pretty ugly, but...
So it's a Yangian of G.
So it is the Yangian of G or G tilde. But I think people usually call it the Yangian of G. Notice that G could be a Kac-Moody algebra. Right. OK, so here's a theorem. So first of all, something reassuring. If you want to get presentation by generators and relations, this is actually even without that. Yeah, OK, let me just, don't worry about it. This is generated by H star T lambda alpha for alpha in the set of alpha i's. Okay, so the generators correspond to these one-dimensional representations of the pre-projective algebra.
You assume they go without loops?
I am working with the localization, and then I am invoking the Swiss deity in the area. OK, so this is proved by myself and Vassereau. And so as Francesco mentioned, we proved it with a larger set of generators, that when you have loops for the quiver, edge loops, then you have to include all the dimension vector at the vertex with an edge loop. But then Negutz managed to remove that restriction. So, OK, at least the algebra is generated. So it makes sense to look at relations. And then, so the map from H star T lambda Q to H star T rep Q bar, okay, identifies lock. Identifies H star T lambda Q, or this one, with what's called a small shuffle algebra. So again, I don't want to define exactly what this algebra is, but let me say that it's very easy to compute the localized cohomology of this thing. okay, because it's just a vector space. It's just a vector space quotient by a group. And so it's easy to get what this space is. And then this map, okay, we can localize. And then localize with respect to T, right? So this map is an algebra map if I put a certain algebra structure here, which is an explicit algebra structure given by a big kernel. Okay, I'm not going to explain that. And finally, so this is this is not very difficult. And finally, there exists a presentation of this thing by generators and relations. And so the relations, the generators are these, and the relations are quadratic relations. These are nice. They are very easy to write. And then we have some cubic relations, many cubic relations, and these are known as the wheel conditions, or they correspond to the wheel conditions. And they are a bit more complicated to write. So Daniel wrote them in one particular case for reductive groups instead of GLN. So it has the same flavor. Okay, and this is a result of Negut's, Francesco, and myself. So a big shuffle algebra is, okay, let me say that. So the big shuffle algebra is given as a vector space. So we have the big shuffle algebra. This is a direct sum. Let me see if I can remember. So it's the space of, let's just write the very big shuffle algebra. No. Let's not do that. Zi1, Zidi. Okay, so you have a bunch of variables I in I. And this is the sum over all D. And here, that's all. And then you should take the invariant under S, the product of the symmetric group. So you have a tensor product of algebra of symmetric functions for every vertex. And the number of variables is the dimension vector. And you take the direct sum for all dimension vectors. And then there's a product, P of Z times Q of Z. These may be different dimension vectors. So let me just say ZD to mention that this corresponds to a piece in the graded component of degree D. ZE. Then this is going to be a big sum over all permutations. Again, D plus E. This is product of symmetric groups. And then I have, so sigma applied to P of D, P of ZD. This is nice. Q of Z, let's say, okay, this is, okay, let me be a bit imprecise. And here we have a big kernel. Okay, so this is the definition of the product. And then the small shuffle algebra is whatever is generated by the big shuffle algebra, but in degree alpha I. Okay, so you define a big algebra. The size of the algebra is given like that, but there's a complicated product. It's certainly not generated in degree 1, and the small shuffle algebra, which is hell to describe, is the thing generated in degree 1. The small shuffle algebra is the image of the morphism, yes. Yes, over the fraction field is given by these wheel conditions, cubic relations. You have to say that as polynomials, it should vanish along a certain family of codimension 2 subvarieties. Sorry? Yes. So that's what when somebody asked me the difference between shuffle and small shuffle, I was about to say that I'm cheating a little bit. We did this in the K-theoretic version, but it's expected that the same proof, if somebody dares to actually go through the details, it should work also in the homology. So yes, for K-theory. Okay, so that's what we know, and also maybe I should say. So it's not let's say very well. It is concrete, but it's hard to work with these algebras. And also I should say I should continue the theorem. So I just erased what. Okay. So for if Q is finite or affine, then in these cases, it is known that H star T lambda log is usual Yangian, respectively affine Yangian. Okay, so in these cases, the torus, the action of the torus can be reduced just because the quiver by some gauge transformation to some very small number of variables, and then we recover the usual Yangian or the affine Yangian. But beyond these cases, I don't think they have been studied very well. Okay. So, in general, it's a very hard problem, but things become much nicer when we take a part of the torus which is symplectic. So if we suppose that we restrict to a subtorus which acts, which does not scale the symplectic form, then all of a sudden things look much nicer. I wouldn't say that everything is understood by far, but it's at least much nicer. So, okay, assume that T acts by preserving the symplectic form. So you could call this the 2 Calabi-Yau case. Okay, so it could be that T is trivial. Okay, that would be already interesting. So here's the theorem. So a very close statement was proven by Davison, Enkar, and Schlegel-Meyer. And then this theorem appears in the work by Davison, Enkar, and then Kinjo, and myself and Eric. Okay, I write Kinjo because I think it's the first time his name appears. And then actually Shivang explained the construction also yesterday. So it will appear in his thesis. It says that this rep pi q, no localization, okay? This is isomorphic to the enveloping algebra of a certain Lie algebra, which we call the BPS Lie algebra, affinized BPS Lie algebra. And this is a direct sum over all D of G BPS D, and the G hat BPS as a vector space, it's isomorphic to another subalgebra, GD bracket U, but just as a vector space. Okay.
Yeah, there is a equivariant on the left-hand side or not?
Ah, sorry, here there's a, there, yes, you have to, yes. The Lie algebra depends on the torus. Okay, there is a dependence on the torus. Yep. Okay, and moreover, so there are two algebras. So moreover, GTD is a subalgebra, a Lie subalgebra. This is the usual BPS Lie algebra. And so this Lie algebra, and so here this is just a result of Ben, Lucien, and Sébastien. This Lie algebra, GT, sorry, sum over D, and this is 2, is a Borchertz algebra. So it's a generalized Kac-Moody algebra. And out of all this, of course, you get, let's say T equals 1, the graded dimension of this BPS Lie algebra, G tilde, G hat BPS is equal, so the sum over D, Z to the D, D, this is, no. This is exactly the Katz polynomial evaluated at T. Okay, so the dimension of the ith graded piece is the coefficient of T to the I in this Katz polynomial. So this, we don't really know what is the quantum group. It's pretty horrible to get it by generators and relations. But the classical limit, let's say, is absolutely the best thing we could expect. Okay, it's a generalized Borchertz algebra, and the graded dimension is precisely given by this Katz polynomial. And moreover, finally, this is again the work of Ben, Lucien, and Sébastien. And I'm not going to write it in details because, okay, so the generators, simple generators, in other words, the Cartan matrix, if you want, Cartan matrix of this non-affinized BPS Lie algebra, right? This G, at least T equals 1, but I think it's, GT. This Borchertz algebra encode the intersection homology of the coarse moduli space of representations of pi q coarse moduli space. So if you're not interested in stacks, but really coarse moduli spaces of representations, then the knowledge of this Katz polynomial gives you the knowledge of the intersection cohomology of these coarse moduli spaces. Okay.
Small comment.
Yes.
For number 3, you need to modify a little bit. So you have to remove the hats. It's just BPS inversion.
Yes. Thank you.
It's the reciprocal of the Katz polynomial.
And maybe it's
So you have to put T minus 1.
and T to the power.
Yeah. So you get Katz polynomial if you take the bipotent, the lambda instead of the
Yes. Okay. Thank you. T to the dd, something like that. Yes, so there, yes. There is a version for rep pi q, there is a version for the nilpotent. And then for one of them, you have the Katz polynomial, for the other one, you have the nilpotent version of the Katz polynomial. Sorry? Yes, Poincaré duality or Verdier duality, yeah.
May I ask, so your comment that you said that doesn't quite work in the quantum version, do you just mean then I have a torus action on?
So if the torus is not symplectic, then what you get is a deformation of this algebra. But to be honest, I don't really have a good feeling for how to treat the deformation of this algebra.
So there's no UQ when it's symplectic?
When the torus is symplectic, there's no UQ. It's just an enveloping algebra of a Lie algebra. When it's not symplectic,
Like geometrically, there's no explication in terms of the homology.
so I mean, okay, so here's okay, let me state a theorem. I did not really want to go there, but let me state the theorem anyway. Because if I want to give some overview, I have to give everything. So here's another theorem, but it's just going to be a remark, okay? Because so the remark is that so in general, for general quiver and general torus, this H star T rep pi q. Okay, and then you kind of you tensor it with some ring of tautological classes, and then you tensor it with H star T lambda q, maybe opposite, and you define an algebra structure on that. Okay, this is isomorphic to the Mollico-Kunkov-Yangian. So this Yangian is defined geometrically. So I guess this is one way to geometrically, I mean, not stacks, but actual moduli spaces to interpret this algebra for any torus. If you like this construction of Mollico-Kunkov, who construct quantum groups out of symplectic resolutions, then here the symplectic resolution of the Nakajima quiver varieties. So there's this isomorphism. And moreover, the BPS Lie algebra, GBPS, non-affinized, is isomorphic to, let's say, well, the way I wrote it, to the positive half of Mollico-Kunkov Lie algebra. Let's say, yeah, all these are positive halves, right? So this result, the first part, is due to myself, Vasro, and also Maria Botta and Davison. Sorry? Tommaso. Maria Botta. Tommaso. It's a name, okay. Tommaso Maria Botta. And the second part is just their work. Oops. Yep. Okay, anyway. So this is why I said that hopefully all Yangians are the same. At least the Mollico-Kunkov Yangians are the same as these Yangians. And then we hope that the Yangians defined by generators and relations are actually the same also.
But so like up there, you're saying that the correct deformation of this G hat BPS is this full like tensor product of stuff. And
so the Coha only constructs a positive half of a quantum group. And the Mollico-Kunkov Yangian is the full quantum group. It's very important. It's very hard, actually. Actually, a consequence of that is that you can define positive half in the Mollico-Kunkov Yangian. Otherwise, their construction is not. It's not easy to get a triangular decomposition. Yeah. So what I'm saying is that you should view this algebra or this algebra as quantum deformations of the enveloping algebra of this BPS Lie algebra.
And they're like the positive and negative halves.
And yes, you can build the Moleko-Kunkov by, you know, it's a nice self-dual object, the Moleko-Kunkov. So, yeah.
And I had another question. This like usual Yangian, is there some statement about how it fits in as like?
Yeah, so you have a morphism from the usual Yangian to. So the usual Yangian is usually not defined for generic T, just for a very specific T. So if you choose this specific T, you have a morphism from the usual Yangian to the Coha. And when the quiver is without loop. And you just hope that it's an isomorphism. But this seems like a really, you know, difficult algebraic problem.
You hope that?
I would hope that it's an isomorphism, but you should ask André Negutz. He would be the one with the most intuition about that.
But in the case of finite, fine, and one loop quiver, all coincide.
Yes, yep.
As in like isomorphism to the molecule.
That works all the time. And if you want to get the presentation in terms of the usual Yangian, then that works. Finite, affine, including one loop quiver. Okay, how much time do I have left?
9 minutes.
9 minutes, okay. So I think I just want to use these 9 minutes to tell you very roughly what we know in the context of curves, when we pass from quivers to curves. So I should say that there's one thing here that we still don't know. Okay, I should emphasize that we know what is the structure of the BPS Lie algebra, but the affinized BPS Lie algebra we don't know, right? So as I said, it's not just this is just an isomorphism of vector spaces, not of Lie algebra. Okay, so that's I think an important question to understand precisely what is the Lie algebra structure that we get here. And the only case that I know beyond affine type, which is kind of like affine type, is what I will talk tomorrow, the case of a surface, zero-dimensional sheaves on the surface. It's kind of like an affine type still. Okay. So very quickly, what do we know of the curve situation? Okay, so from quivers to curves. Okay, so if you remember, there was this first purely combinatorial K0. So now we consider the category. So now we replace everywhere representation Q by the stack of coherent sheaves on X. So X is a smooth projective curve of genus G. So rep Q goes to coh X, and then T star rep Q goes to the moduli stack of Higgs bundles in X, and then this Lustig Lagrangian goes to the global nilpotent cone, lambda X. Global nilpotent cone. So maybe I should say a few words. So coherent sheaves on X, everybody knows what this is. Higgs sheaves, this is the, if you want, this is the same thing as coherent sheaves with proper support on T star of X. Okay, so maybe you can think of it like that. These are one-dimensional sheaves on T star of X with proper support, so they are not allowed to go to infinity. And this is just also the set of pairs, a coherent sheaf and a twisted endomorphism. Okay, but you should really view this as the Calabi-Yau situation of the moduli spaces that were considered this morning. Okay, Junliang considered exactly one-dimensional sheaves on P2, and this would be one-dimensional sheaves on T star of X. Okay, on a symplectic surface of this kind. And what is this? This is just the set of one-dimensional sheaves supported on the zero section, or you can just say the set of pairs f phi such that phi is nilpotent in the appropriate sense. Okay, when you compose it many times, you get into f tensor kx to some power, but at some point it should be 0. Okay, so maybe what do we know? So what is k0? Well, k0 is z square. Okay, it's much smaller than in the quiver case. And what is the symmetrized Euler form? It's like this. The class of a point is in the kernel, and then I should have 2 minus 2g. Okay, so there's not so much information to gain from that, right? Except that this looks like affinization, by which I mean I just added a bunch of zeros, of the G-loop quiver. Okay, the Euler form of this G-loop quiver is just 2 minus 2g. Okay, I have one and I have one endomorphism of the simple object, and then I have g extensions of that simple object. Okay, so we can expect something related to the affinization of the Kac-Moody algebra, Borchert's algebra associated with that. Okay, then, so this was level 0, and now in level 1 we have the whole algebra. So maybe still in level 0, let me just say that there exists a Katz polynomial counting, there exists a Katz polynomial counting absolutely indecomposable vector bundles of rank R and degree D. And let me just denote it by AG because it can be shown to only depend on the genus. And R, and in fact it just depends on R, but let me just say right ARD. And this is the evaluation of that polynomial on the Weil numbers of the curve. So Katz polynomials, of course, you're counting points over finite fields. So your curve is defined over finite field. And so it has some Weil number that give you the zeta function of the curve. And this is a polynomial in the zeta function of the curve, if you want. Okay, so that exists. And then there exists, so we can define the whole algebra of xg over fq, and we can define also the geometric whole algebra. Hopefully Jiang Fan in his PhD thesis will prove that this is the same as the what I denoted K prime, the sub-algebra generated just by monomials. But anyway, these exist and are, let's say, well understood. So here we have a presentation. When G is of genus 0, we get the usual quantum group, UQ SL2 hat, which is compatible with this description. When G is 1, we get the so-called elliptic whole algebra. And when G is of higher genus, we get something. But there's a presentation. But what I think would be even more interesting, and I really have to stop now, is so there exists also the Coha, so the Borel-Moore homology of the stack of all Higgs bundles with the product, or rank and degree, RT. There is also a nilpotent version of that. Okay, and so this recent work with Davison, Kinjo, Lucien, and Eric, we show that this is actually isomorphic up to some completion to the enveloping algebra of a certain Lie algebra. GRD, let's call it hat BPS. Okay, so there exists a BPS Lie algebra, and this is a graded Lie algebra. This is a graded Lie algebra. The grading also involves the Veil numbers in some way that I don't want to explain. And we don't even know what is the piece of degree 0. Okay, so let me just stop at that. So we know some things, you know, the semi-stable version and something like that, but I think it's more interesting to study the entire whole algebra. And I just want to end with this question that I don't know the answer to, and I really love to. And I think it's a very, you know, the object that you should get as an answer should be nice and clean. So the question is, what is the Lie algebra structure on, let's say, well, what is the, yes, Lie algebra structure on the direct sum for all rank and degree of the degree 0 part. Degree 0 part, and what we know, let's call this G0. Let's call this that. And so what we know is that the enveloping algebra of this is just the algebra of top. It's just constructed from the top dimensional component of this global nilpotent cone. Okay, maybe again there's some degree. You have to be careful about the degree, but yes. So you take a curve of genus G, you have this global nilpotent cone. There's a Lie algebra structure on the H top. You can describe all the irreducible components nicely. There's a Lie algebra structure that should be the enveloping algebra of a certain nice Lie algebra. I just don't know what it is. And I think it would be the first step in understanding better this algebra. And I really should stop here, so sorry.